Unit 4, pages 80 to 87, Solubility Rules. In order for salts to ionize in water, energy must be used to pull the ions in the crystal apart from one another. Some energy is released when the ions become solvated or surrounded by water molecules. For now, it is enough to know that if the net energy required to separate the atoms is too large, the process will not occur, and the material is not soluble. The second law of thermodynamics is required to explain this result and will be discussed in Chapter 19. Here are the rules that govern which ionic materials are soluble in water. Note the diagram at the left, that you have mostly solid here and very few particles there, which would mean this has a low solubility. Very little of the solid dissolves. So you might recall this chart, which is the solubility rules, and it's explaining that if you have a group 1 metal, salt, or ammonium, or nitrate, perchlorates, or acetates, anions, then it's going to be automatically soluble with no exceptions. If you have chloride, bromide, or iodide, it's going to be soluble unless it starts with one of these cations, which is going to make it insoluble. If you have a sulfate ion, it's soluble unless it's paired with one of these cations, and it becomes insoluble. These are going to be insoluble automatically unless they are paired with a group 1 metal, ammonium, or one of these alkali and earth metals. Same thing here, here, and here. It says that you have to memorize this chart. However, the odds are very good you're going to actually get it for any exams. So example 4.27, which of these salts are soluble and which are insoluble in water? So sodium chloride has a group 1 metal, so it's automatically going to be completely soluble. Silver bromide. Bromide is soluble except with silver, so we're going to make this an insoluble compound. Lead nitrate. Anything with nitrate is automatically soluble with no exceptions. We have potassium sulfate. Sulfates are soluble, and there's no exception when you have a group 1 metal. Or you could even just say, hey, because there's a group 1 metal here, it's automatically soluble. And then lastly, calcium sulfide. Notice that sulfides are in the insoluble column, but calcium is an exception. So instead of being insoluble, it's going to be the opposite. It will be soluble. Now on to net ionic equations. Silver nitrate and sodium chloride are both soluble in water. However, when they are mixed, the insoluble compound silver chloride is formed. Since silver chloride is insoluble, it forms a solid material called a precipitate that falls out of the solution. Here is the overall reaction. Silver nitrate, which is able to dissolve in water, soluble, and sodium chloride, also soluble, and when you place them in a beaker together, then you're going to have a double replacement where the silver and the chloride get together, and because they are insoluble, we label this as solid. This is the precipitate. And then your sodium and your nitrate ions are going to be considered the spectators of this because they remain aqueous or dissolved in the solution. The reaction equation that describes the actual chemical changes that occur in this reaction is as follows. Silver and the chloride make the precipitate. So this is called the net ionic equation because it represents the only thing that actually changes in this system. A reaction written in this way is called a net ionic equation. It shows only the chemical species that change in the reaction. Notice the sodium aqueous and the nitrate aqueous are not included in the net ionic reaction. They are spectator ions and do not change chemically in any way during the reaction. Very often the focus is going to be what's in the beaker. So notice that the original beaker of sodium chloride aqueous shows dissolved sodiums and chloride ions, and then the aqueous silver nitrate in its own beaker are silvers and nitrate ions. When you mix the two beakers together, all of the silvers and the chlorides combine and form a solid down here. And normally I would kind of have a little bump to show that that's a pile of solid at the bottom of the beaker. And then notice your spectator ions remain aqueous, sodium and nitrate. They remain separated in the solution surrounded by water. Writing net ionic equations, you're going to start with a balanced overall reaction, such as this one. Everything that you label soluble or aqueous is able to dissolve and should be broken apart into its individual ions, such as magnesium and 2 bromide ions would be written as such. And then 2 sodiums and 1 carbonate ion, they're aqueous, so they would be written like this. So that's all of your reactants broken up from one another. Then your products, this remains a solid, so it should not be broken apart. It remains intact. And then we're going to have 2, because the coefficient of 2 sodiums and 2 bromides here and here. Notice you have a balance equation where you have 2 of each sodium ion and 2 of each bromide ion. Because magnesium carbonate is the precipitate, it is going to be used to write the net ionic equation, and automatically that makes sodium and bromide the spectator ions. So if you cross out all of the spectator ions, then magnesium plus carbonate yield the precipitate magnesium carbonate. This is your net ionic equation. So example 4.28, write the net ionic equation for this reaction here. So I'm going to have sodium sulfide aqueous plus zinc sulfate aqueous yields. And if you want, you could actually go ahead and break these up from one another. You're going to have 2 sodium ions. You don't have to write the aqueous after everything. We're going to assume this is aqueous if they're broken apart into ions. You have 1 sulfide negative ion. You have 1 zinc ion. And you have 1 sulfate ion. So what is this going to yield? Where you're going to have your sodium and your sulfate would hook up and make sodium sulfate. Plus 1 minus 2 puts that 2 right there to balance the ratio. And you're going to get zinc sulfide. Plus 2 minus 2 cancel. Notice on your solubility rules that because that's a group 1 metal, it's automatically soluble. And soluble means you would label it as aqueous, which means that over here it's going to be broken apart, remain separated in solution, 2 sodium ions and 1 sulfate ion. And then this, sulfides are insoluble and zinc is not an exception. So this is going to be your precipitate because it is insoluble. And that is going to be written down here without breaking it apart. So my spectator ions are the sodium and the sulfate, and the precipitate is the zinc sulfide. So I'm going to write my net equation for the zinc sulfide. You have zinc combined with the sulfide to form your precipitate zinc sulfide. I just wrote the solid there for technicality because it is the precipitate. And if you wanted to be very technical, both of these are aqueous to begin with. But again, you don't have to include the phase notations. Writing it as a net equation is just assumed these are aqueous and that one's solid. So types of solution reactions. Exchange reactions, also known as metathesis reactions, also known as double replacement reactions, involve the exchange of positive ions from one compound with negative ions from another compound. In the example below, copper plus 2 ion from CuCl2 combines with sulfide ion from potassium sulfide to make the product copper sulfide, which is our precipitate because it is solid. So here's just showing you that you would combine the potassium and the chloride here, and then the copper and the sulfide here. That's soluble, so it's aqueous, and that's solid, so it's the precipitate. Common mistake. Notice in the balanced exchange reaction below, the subscripts in the reactant compounds are not the same as the subscripts in the product compounds. Subscripts, that's the little numbers here, depend on the charges of the ions combined to make the compound. To find the subscripts in the product compounds, you have to consider the charges on both ions in the product compound. In the figure below, the method of crossing the charges is used to find the subscripts. Meaning, since copper is plus 3 and chloride is minus 1, you have to balance the charges. It's going to take 3 -1 chlorides to balance this 1 copper plus 3. And that's why there's a subscript of 3 here. Over here, copper is a plus 3, sulfide is a minus 2. Common factor of 2 and 3 is 6. So you're going to need 3 times 2 coppers, subscript of 2 here, in order to make a positive 6. And -2 times 3 equals my -6 in order to balance the charges. And so that is why these subscripts are what they are, from balancing the charges. After which you change coefficients in order to balance the actual equation. In an acid-base neutralization reaction, you have an acid, which starts with hydrogen, and a base, which ends in hydroxide, and it is essentially a double replacement. Hydrogen and hydroxide make water, and sodium and chloride are our salt. If you were to write the net ionic equation for this reaction, the net chemical change is the neutralization of the acid hydrogen and the base hydroxide to make water. And this here actually would be referred to as a liquid, not aqueous, because you can't have water dissolved in water. So it should be a pure liquid. So because this is the pure liquid as opposed to the solid precipitate, then everything making this water is going to be what is in our net equation. Hydrogen plus hydroxide yields water. This will always be the net equation when it comes to an acid-base neutralization reaction. Homogeneous solutions have the same composition throughout the mixture. A salt dissolved in pure water is an example of a homogeneous solution. The composition of heterogeneous solutions varies from point to point throughout the mixture. River water is an example of a heterogeneous solution. There is sand, bug parts, and so on at different points throughout the mixture. Air is an example of a heterogeneous mixture since certain regions have higher concentrations of perfume, smoke, etc. So the two solubility rules that you should absolutely memorize, at least for the AP test, because these are the only two that they worry about, is that anything with a group 1 metal is going to automatically be soluble. And anytime you see a nitrate, that is also automatically soluble. Otherwise, on your LSU exam, you'll be given the solubility rules. Net equations are written for the formation of a precipitate, which is an insoluble product, as well as the formation of water in an acid-base reaction, according to these notes so far. Spectator ions do not participate in a chemical reaction and appear identical on both sides of the equations.